Okay, so this is what we're trying to do today. Okay, so last time we actually made some kind of introduction to the nested cells theorem. Okay, so we began with the the initial definition. So first things we define is what we call a sequence of cells, which is nested. So a sequence of cell is nested. It means that there's a chain of inclusion hold. So I1 contains I2 and contains I3 and so on. So each I is an interval, like I is equal to AN to BN is a closed interval. Okay. So in this chapter, when we talk about nested cells property, we're all talking about the closed interval. Of course, the same concept can be applied to the open interval. But however, if you use a sequence of open interval, even though it is nested, but it's not going to carry this nested cells properties. Okay, so this property is only for closed interval. Okay, and we have also talked about the examples, right? Some example we have talked about this last time, so I don't have to. Actually, I don't have to repeat. So here, so the main thing today we want to do is we want to prove this nested cells property. So this cells property says that suppose you have a sequence of nested cells, okay, carries nested properties. Of course, assuming they're non-empty closed cells in the sequence. And then the result is that if you make an intersection of all these intervals in the sequence, then this intersection cannot be empty. So this is the nested cells property. It's extremely important. Now it is so important that this property is somehow equivalent to the completeness property. So you see, our foundation is the completeness property, right? So from this foundation of completeness property, we build several results. Now it's reached to nested cells property. And then there is a proof, but I don't think we'll have time to talk about this. It's that, well, of course, this, you think about this logic flow, the completeness properties, that's our foundation, now implies the nested cells property. Now, there is a proof one can use to show that if at the beginning we don't assume the completeness property, instead we're assuming something new. For instance, if I assuming I laid foundation to be by assuming nested cells property, I take nested cells property as our foundation, then you can prove that this nested cells property will imply the completeness property. So in some sense, these two properties are equivalent. So that's why the nested cells property is so important. Okay, in the later chapter, you will see some extension about this nested cells property in a high dimension case, or even in a more general setting. Okay, it's very important. Okay, so let's see. So today we're trying to consider this special case in the one-dimensional case, where you see that why the intersection of Rn is always going to be non-empty. All right, and last time we also see some example to show that. So, actually from this example we see this is true because the intersection is not empty. Okay, but however, this example cannot replace our proof. So our proof has to be under the general setting to see for a general sequence of nested cells sequence why this intersection is not empty. Now in this theorem, we assume that all the cells are closed, and this is important. Okay, now without closeness, this result is not necessarily hold. So actually, we also see example. So in some case, you can see the intersection will still not empty, but in some case, you can see the intersection will become empty. So without smoothness, without closeness assumption, we cannot have any definite result about this sequence of nested cell. Okay, so in general, we make this closeness assumption. Okay, all right. So now let's look at how we can prove it. So this is something we want to prove. Okay, so first, let's say that IN. So we have a sequence of IN. IN equals AN and BN. Okay, now first we observe that we have assumptions here saying that the sequence is nested. Now what does it imply? What the nested assumption tell us? It tells us that since IN is made up by AN and BN, so if the IN is nested, then this means that AN is increasing and BN is decreasing. Now here we're not talking about strictly increasing or strictly decreasing, because IN can equal in the sequence, right? Some IN can repeat itself. Okay, so when we say the sequence is increasing, this means that the AN sequence AN is non-decreasing. And we say BN is decreasing, we say that BN is non-increasing. So this is the meaning of that. And then you look at the picture, this is obviously true, because if sequence nested, you can see AN is increasing to the right side and BN is decreasing to the left side, right? It's so clear, okay. Now here we want to make a crucial observation, okay? The observation is that we're going to have this inequality. Now why this inequality, what this inequality means? So this inequality is made by three inequality, okay? Now the first inequality on the left side, AN, so here I'm choosing integers, N and M. Now first inequality is saying that AN is less than equals to AN plus M. So you have additional M in the second term. So this means the index for the second term is greater. So this means that because AN is increasing, so therefore naturally AN is less or equal than AN plus M, right? Obvious, this is true. Then the middle inequality, so AN plus M is less or equal than BN plus N. So these two things carry the same index. Now this is obviously true because A represents the left endpoint and B represents the right endpoint. For a given interval, the left endpoint is always less or equal than the right endpoint. So the middle interval is obviously true. Now look at the third interval. Third interval that because AN, so third interval that BN plus M is now less equal than BM. Okay, I'm not using N anymore. I use BM for our purpose. Now the third inequality is still true is because that BM sequence is a decreasing sequence. So when index getting bigger, the value is getting smaller. Okay, so therefore you can see that based on the monotonic properties of AN and BN, we can obviously have this inequality. Now the reason, so the key things we want to observe is the first term of this inequality and the last term of the inequality. The middle term, like AN plus M or BN plus M, that's not important. But however, when we get this inequality, we have to pass, it's like a bridge. We have to use this, okay? Now the real things we want to observe from here is that AN is less equal than BM, okay? Now here is N and M are just integer, but here they are arbitrary integer. So no matter what kind of N you have or M you have, they always hold. So AN is always less or equal than BM. So this is the observation we want to make first, okay? Now what does observation tell us? This observation simply means the following. So it means that the AN sequence and the BN sequence are completely separate. So AN is on the left side, and BN is on the right side. They cannot cross to each other. They cannot cross the line. So between them, there's a gap. Okay, they cannot cross. AN is small sequence. BN is completely separated to be a bigger sequence. Even though it's decreasing, it's bigger. So you can look at the graph here. So AN is like A1, A2, A3, AN, always on one side. Then B1, B2, even B sequence decreasing, but now the B term is going to enter the area of the AN terms. They are completely separated. Okay, now this is important. Now because of this, you can see that you can see two things. Okay, one thing is that the AN sequence is bounded above. Why the AN sequence bounded above? Because you can see all the B term become the upper bound of AN, the sequence of AN. Obviously, AN is bounded above. And for the same reason, the sequence of BN is bounded below, because that every term from the AN sequence will become a lower bound for the B sequence. So these two sequences, one is bounded above, one is bounded below, obviously. Now, by the completeness properties, we know that every bounded above sequence carries the least upper bound, right? So obviously AN will carry its least upper bound. And so we denote C to be the least upper bound for AN. And the BN sequence is bounded below, so therefore, based on the completeness property, so this thing carries a greatest lower bound. So I denote eta to denote this greatest lower bound. Okay, now I'm going to label these two. So I have two new numbers. C, because C is the least upper bound for AN, and eta is the greatest lower bound for the BN. So I'm going to label these two upper bound and lower bound, okay, or what we call supremum and infimum, onto this axis. So where we should put it? Where are they? Where we should put it? Obviously, okay, C has to be on control the whole sequence, right? The eta or below or the B sequence, okay? So have to, but here we put C is on the left side of eta. So this means that when we enter these two number into the axis, we have already assumed that C is less equal than eta, okay? Now this is kind of obvious. Why? Because the complete sequence of AN is on the left side of the B sequence. So the C has to be below the B sequence, right? And the eta has to be above the A sequence. So somehow this is obvious, okay? Well, we still need to have an argument to prove it. And actually, and this is exactly what we want to get. This picture is exactly what we want to reach. So once we reach to this picture, you can prove the result. Okay, so now let's see why C is always on the left side of eta. Okay, now the reason is because our previous inequality, AN is always less or equal to BN for arbitrary N and M. Okay, so let's see the reason, more detailed the reason. Okay. Now, so let's start from this inequality. So based on this inequality, AN is less or equal to BM. Okay, so we notice that this is true for any N and M. Okay, so this means that for any M, so you first think about somehow you fix the N. Okay, you fix the index N, and you can think that for every M, okay, and this BM is going to be the upper bound for AN. Because you can see that no matter what kind of N you choose, okay, all the term AN is always less or equal than BM. No matter, okay, so this means that, so every BM will be an upper bound of AN, okay? It's obviously is implied by this inequality. Okay, now C is what? C is the greatest lower bound, right? No, it's the least upper bound. Okay, so BM is always the upper bound, and C is the least upper bound. Obviously, C has to be less or equal to BM for any M. Okay, there shouldn't be any question, right? Obviously, so this is the detailed observation. You have to get this from that previous inequality. Okay, now once we get this, okay, then you look at the BM. Okay, so now you can see that the C now becomes a lower bound for BM. Okay, so here I change the index from M to N, it doesn't matter. So the key is that no matter what M you choose, or no matter what N you choose, the C is always lower than this time. So C itself has to be the lower bound of BM. The C may not be the greatest lower bound, but C itself has to be the lower bound. And now think about eta. Eta is the greatest lower bound. Obviously, eta has to be greater than or equal to C, because C is the lower bound. Eta is the greatest lower bound. Obviously, so this is going to be true. So this proves that the C is always on the left side of eta. Okay, so this means that for any n, now you can see for any n, you have this result. An is less or equal than C, because C is the upper bound. C now less equal than eta is because of the proof, which is prove this. And eta is less or equal than Bn. So this means that now you can see the interval, think about interval C to eta, this closed interval. This closed interval belongs to any Rn in the sequence. This closed interval belongs to any Rn in the sequence. So therefore, this closed interval will also in the intersection of all the intervals. Okay. So from here, immediate conclusion is that this intersection cannot be empty. Because you can see the intersection carries a closed interval, the whole interval there. Every point in this closed interval will be belongs to the intersection. How can this intersection become the empty set? It's impossible, right? So therefore, we're not just showing the intersection is non-empty, but we also show that we have a closer view on this intersection. This intersection will contains an entire interval C to eta. Okay, C to eta. So you can see this whole interval is in the intersection. This automatically implies that this is non-empty. Now here I have a question for you. Okay, so the proof is pretty clear. Okay, now suppose you can think that how big the interval is, the C to eta, how big the interval is. Well, it depends on your sequence, right? Now my question is, suppose the sequence of interval, the Rn, suppose the length of Rn goes to 0. Suppose the length of Rn goes to 0. Okay? What can you say from this result? This will imply that the C to eta, this middle interval, will shrink to a single point. Or shrink to a single point. Right? And the intersection, therefore the intersection maybe will only contain one single point. Okay, because of the Rn the length of Rn will approach to 0. Well, this is something you can think about it. Okay, when you review for this proof, you can think that how you can prove this from the nested cells properties. Okay, an interesting question. Okay. All right, so this is the proof of nested cells property, and actually there is an additional result related to nested cells. You can see here, based on this proof, and what we got is C to eta contains in the intersection, right? So this is enough for us to conclude that the intersection is not empty. But we want to learn more. We want to understand more. So what is exactly the relation between this interval C to eta and the intersection? Actually, what we can show is that C to eta are not just contained in this intersection, but also this interval is exactly equals to this intersection. So now we have a very nice picture. So what is if you have nested cells property, and how do you look at it? How do you understand this intersection? We know this intersection is not empty, but how do you describe this intersection? This intersection is just equals to what? Just equals to the interval C to eta, and we have definition for C and eta. C is the supremum of An, and eta is the infimum of Bn. So you have a complete picture of this intersection. Okay, so now let's see how we can prove this. Okay, now proof is based on the so from the previous result, we know that this interval already contained in this intersection. So therefore, what we need to show is that this intersection is also contained in this interval, right? Remember in the Math 415 when we talk about set theory, how do you show two sets are exactly equal? So you have to show one set contains the other, and also vice versa, right? So we have done halfway. So the things remaining to show is that the intersection is contained in C and eta. Okay. Now how we can achieve this? we are going to use the method of contradiction. Okay. Now, using the method of contradiction, suppose the conclusion doesn't hold. Now, what do you mean the conclusion doesn't hold? This means that there's some point. I mean, what does it mean is that this intersection is not contained in this interval, C to eta. So if not contained, so this means that there is a C in the intersection, but this C is not in the interval C to eta. Okay, we can do that, right? So this is a if we assume the opposite, then such C always exists. Okay. Okay, then you have to divide into two cases. Then this C is not in this closed interval. What does it mean? Either the C is on the left side of the they have to be outside of the interval. Then the C has to be on the left side or the right side, right? Two cases. So it is, suppose the C is on the left side. So this means that you're assuming C is less than C. The other case is that C is greater than eta. Okay, but however, the proof are just parallel. So I'm just only showing you how we can reach the contradictions by assuming C is less than C. Okay, so let's assume this. So this means that in the picture, you can see that C is now on the left side of C, eta, okay, on the left side. So what does it mean? So when a C is less than C, what does it mean? So in order to from here to conclude something, you have to understand the meaning of C, okay? What is C here? C is the least upper bound, okay? Now, if the C is less than this least upper bound, so this just means that C is no longer C is not an upper bound for AN. Okay, C cannot be upper bound because C is the least upper bound. And so this means that by theorem 1.5 or by the definition, your choice. Okay, so this means that there must be an AN. So this means there must be an index N so that the term AN is on the right side of C, strictly greater than. Okay, otherwise, if no such term exists, so this just claims that C is upper bound, then obviously we're not assuming this. So by assuming C is less than C, C is not upper bound, then naturally we can imply that there is AN greater than C. And then you can see that this will imply that the C is not going to be in the interval AN to BN, right? It's just like the picture shows. C is not going to be inside, belongs to the AN and BN. And this will contradict to the C has to be in the intersection. Now, because C is coming from the intersection, okay? C is coming from intersection, this means that C has to be, C must belongs to any RN, that belongs to any AN, BN. But here, we got some result that C is not in AN. For certain index, C is not in AN, BN. So this will contradict to the choice that the C is coming from the intersection. That's a contradiction. Okay. So that's a proof. So we assume the opposite, then we get a contradiction. So that's the result we get. Okay. And actually, I just mentioned ago that it is possible that C is greater than eta, right? If that happens, then actually you are going through the same proof, same argument. Okay, you can check it. Now, the homework, in our homework section, I didn't include any homework related to the nested cells theorem. So for this part, the example I'm showing you, this example or similar example will be important. Okay, and also so this missing part of the proof, you may also want to think about it and finish it by yourself. Okay, and also I'll mention that the think about this result, think about these questions. Suppose the Rn, the length of Rn, okay, tends to 0. So interval getting small, shrink to a single point, for instance. How can you deduce how can you show that the intersection is just contains of one single point? So to prove this, you're not going through the entire proof, right? You can use the existing nested cells property plus this conclusion, additional conclusion. Well, this means that you can assume the fact that the whole intersection is at this interval, C to eta. Okay, you can assume this. Okay, and then you're trying to, then from here, suppose you know that actually the Rn is, well, the length will shrink to 0, getting small. How can you show that the intersection will actually consist of only one point? That means the interval C to eta is just consists of one point. Okay. Maybe next time on Tuesday I will mention further about this, but you need to think about this. Okay, think about it. Now thinking about this kind of problem will help you to prepare to the quiz. All right. Okay, so this is all I have to say today. Okay. Do you have any questions? If no question, and then we can, of course, we can finish now, and we can